Welcome to tutorial 1C, which is going to be about building your initial energy model. And keep in mind that the purpose of this model is really to start to familiarize yourself with the different aspects of energy use in buildings. It's not meant to be the most accurate model, although I'd like to see you try to get it as accurate as possible. The real point of this is for you to start to dig in deep into the different components of energy use and start to recognize some of the limitations and assumptions that you're bringing to the table. So in this tutorial, we're going to cover the process for generating the energy model, and it's really all on this page, page 4 of the assignment. We'll start with entering the information into the Excel spreadsheet, and then I'll walk you through how to generate results. So let's go back to that Excel spreadsheet that you're familiar with by now and go down to the fourth part where it starts with the energy model. And you can see, just as an overall here, you should be used to this by now, what we're looking for is the item that generates energy, or that uses energy, the power that it uses, and the amount of time that it uses. And ultimately what we're going to do is multiply power times time to get energy. And then we're going to deal with that energy in a few different ways. So let's start with these tabs here. We're going to look at cooling, heating, ventilation, lighting, equipment, process loads, and hot water heating. And in your documentation, you'll have more or less some values for each of these. Now, I completely understand if you don't have, say, the power consumption of your cooling system. It's a hard number to find, and it can be unreliable. That said, if you have a number, please go ahead and put it in there, give us the power that it uses, and then estimate the a number of hours per day and the days per year that you're using it. If you don't have the power numbers for your heating, cooling, ventilation systems, then I've got a rule of thumb method you can use to estimate them. If you go over to this HVAC tab, you'll see some instructions about how to go through with this. And keep in mind that these are just rules of thumb. You can see that there's a lot of things that they don't consider. They don't consider the climate, they don't consider the amount of insulation, they don't consider any shade, how many windows you have, what kind of windows. There's all kinds of simplifications in this rule of thumb, as there are in almost any rule of thumb. But this will give you some number at least to think about relative to the benchmark numbers and your utility bills. And then it'll also give you a way of comparing later simulations that you do in the semester that will look in more depth at heating and cooling systems with a lot more inputs. So for now, these rules of thumb are approximate, and they give you a sense of the power draw at peak demand, and then I've also added some average power use as well. These images on the left, you can see the cooling, heating, and ventilation, are meant to give you a sense of what the sort of order of magnitude of these systems are. And they can be, the logic here can be applied to much larger buildings, much larger systems, but at least, I hope at least this gives you some basis in your own experience for understanding what a watt of cooling represents. So, for instance, here, this is a standard residential window unit air conditioner, and that would be sufficient to cool about a 15 square meter room. And that uses about, or that supplies about 1,000 watts of cooling. So for instance, right here, if I input 15 square meters, then that's going to show that 1,000 watts of cooling is required. And then if you read down here vertically, there's a whole bunch of different inputs, and you can choose to use these to change them, or you can accept the defaults if you don't know quite yet what you're doing, which is totally understandable. We'll get to all this later in the semester. But the system efficiency represents how efficient that particular unit is at delivering cool air, in this case getting rid of the heat. Then duct losses, which in this case actually there would be no duct losses, so there'd be 100% efficiency there. Notice that these numbers then, the power use went down as a result. If I go back to 80, then it goes up. 80% duct losses, or sorry, 20% duct losses are typical. And then envelope losses. This is how leaky your building envelope is, and 70% would be a typical rule of thumb number. So what that does is when you multiply all these together, 1,000 watts times 350% times 80% times 70%, or sorry, 1,000 watts divided by these percentages, you get the peak power use. And that would be the power use when the compressor is on and when the fan is on. And all HVAC systems cycle. That means that they turn on for a peak amount of time for some time, and then they come down in power use for other parts of the time. So to get the average, in this case, I'm assuming that the compressor is on for half of the time that the unit is on. You can, based on your knowledge of your own system, you can of course choose to just input the number of hours that it's at peak power, or the number of hours that you think it's at average power. So you're going to take one of these powers uses or numbers and go back to the energy model template, and here under cooling power, type in what you think it is. I think that was right. 510 is what it should be. And then describe what it is. So we'll say bedroom window unit. And I'll say this is on most night times for about 6 hours, and it's on for, say, 2 months a year, which would be 60 days or so. And that gives me a total energy use of 183,000 watt hours, or if you look over here, 184 kilowatt hours per year. So if you then want to add more, say you have more units, say I have another bedroom, and the other bedroom is now 18 square meters. I can move that to 18, and we'll assume that this is, sorry, 306. What did I do here? I've used the peak power instead of the average power. Sorry, I'll correct that right now. So if I go back to 15, that should have said 255. Sorry for the confusion there. That's if I'm using average. And then I'll say this is the master bedroom window unit. And this is also on for 6 hours for 60 days a year. Notice in this case that the total didn't sum right here. And that's because when we added this row, we didn't copy this one. So an easy way to copy this is to take this lower right hand corner, drag it down, and then make sure that this automated the correct cells by clicking up here and then seeing. So yes, it's 306 times 6 times 60 gives you this total. And then also make sure that this is summing the appropriate cells, which it is. So that's a total of 201,900 watt hours per year. And then if you look horizontally here, you can see that this gives you kilowatt hours per square meter per year, the energy cost in US dollars per square meter, and then the amount of photovoltaic you would need relative to your room area to cover all that energy, which in this case is not a lot. So that's kind of an overview of how to deal with the cooling. And the heating and ventilation is really very similar. So if we go back over to heating now, this already has the square meterage, the area of the zone. And keep in mind, right now, these are all linked to the first one. So if I change this one, this will also change, as will the ventilation. But it's entirely possible you'll have some areas of a building that are cooled and other areas that are heated and still others that are just ventilated. So if you want to just override that, you can type in anything you want here and you'll get, it'll break that dependency. So say for a second I did have 50 square meters of heating in the building. This is right now what we're using as a comparison is just a space heater. And these space heaters are usually about 1500 watts and they can heat a small room, essentially about 15 square meters or so. So if I had a space that was 50 square meters, I'd need about 3 of these heaters to do it. Did I do that math right? Yeah. About 3 of those heaters to do it. And in addition, if it's a central heater, like a furnace, that's then transmitting heat through ducts, then I'm going to have duct losses. And in addition, I've got the system efficiency itself. The system efficiency for heating is pretty interesting because it depends quite widely on the type of heater or type of fuel that it's using. Furnaces that burn gas or oil or basically rely on combustion are somewhere in the neighborhood of 70 to 90% efficient. Electrical resistance heating is about 100% efficient. And heat pump heating, which is, well, I'm not going to explain what it is right now. We'll go into it later in the semester. But that's about 250% efficient. So there's a very wide range here, and the results will change by a large margin depending on that. Use your best guess right now. If you have questions, feel free to ask me in class, and we can work it out. Again, I've included both a peak power use and an average power use. And in this case, the average power use is just half of that. Again, like the air conditioner, it primarily depends on how often you're just blowing air as opposed to heating that air actively. So I'm going to, just for the sake of an example, I'm going to use the peak power this time. I'm going to go back to my energy model template. I'm going to use that 11,161 as the peak power, and let's say this is in the bedroom, space heater, and say I use this overnight, so it's on for 12 hours, but it's actually only at peak power for, I can estimate 3 hours of that. So I'm going to estimate 3 hours, and then the heating time happens, say, for 4 months, would be 4 times 30 is 120 days of the year. And then I get the amount of energy that it's using there. Again, same as I said for the cooling, this all automatically fills in. The one thing you do have to be careful of, which I pointed out earlier, is that this cost is tied right now in my spreadsheet to fuel costs. So I can show you it's linked to fuel costs. If you're using electricity, you're going to want to move that up to there. Okay, and lastly, ventilation. Ventilation is this one here, and I should point out that this ventilation rule of thumb is just based on the amount of ventilation that you need for fresh air. It's not hardcore exhaust ventilation. It's not going to clean out a lot of the hot air and replace it with cooler air. It's kind of a background fan that's on most of the time in order to provide enough fresh air. And this is very common for all kinds of buildings, both commercial as well as residential, to have this. And again, if you don't have ducts, then this would be 100% efficient for the ducts. So if I've got 3 watts as my power for my ventilation, I can say it's running 24 hours a day for 365 days, and it's still not very much energy in the greater scheme of things. I'm just going to say exhaust ventilation. There. The next two categories are pretty easy, and you should have a lot of this documentation already complete from the original work that you did. So for lighting and equipment, it's very simply energy is power times energy, and as you just saw in the power monitoring exercise, it works out very simply. And so this energy model is really going to be just as accurate as any other energy model. It's really quite easy to estimate lighting and equipment, assuming you can estimate how many hours you're actually using the stuff. So I'll just give a few examples here for lights. I'll say hallway, bedroom, bath, and the hallway, say, is 100 watts, the bedroom has a total of 40 watts, and the bathroom has a total of 120 watts. And then again, this is probably the hardest part, is estimating the time. I might estimate that the hallway gets used for, in my case, my hallway gets used for less than 10 minutes a day. So what is 10 divided by 60.17? And most days of the year. The bedroom, on the other hand, gets used for maybe an hour a day for most of the year, and the bath gets used for probably a half hour a day. We'll call it an hour a day, half hour during the morning and half hour at night for pretty much every day of the year. Let's call it that again. So this would be my estimate of lighting just for those rooms. Equipment, similar thing. Whatever, computers, cell phones, and if you're struggling to come up with other equipment like I am, I've actually got an equipment list here on this tab, and this will give you a good idea of if you weren't able to document the equipment in the building where that you originally documented, some typical values for different equipments. And I should point out here in this list that there's a few different categories. There's gas versus electric, and there's process versus equipment. And you'll see here, for instance, electric equipment includes all these different things like ceiling fans or electric blankets or shavers or hair dryers or computers, TVs. These are all fairly small loads, and they're fairly consistently used. However, process loads are much more difficult to estimate because they're much larger loads for the most part, and they are very sporadic. So you could use your oven at 7,300 watts for 20 minutes a week. And while the power is very high, the time is very low, so the overall energy use could be quite low. On the other hand, if you're running a commercial kitchen, you could be using that oven at full steam for most days, and that's a significant load on the building. So this is why we have a different category for process loads than we do for equipment, because you'll see when we get into modeling in more detail, the equipment schedules are much more consistent and constant, and the process schedules are much more customized. So enter the power for whatever equipment you come up with for your analysis zones, and then the time that you've got them, that you're using them. In the case of something like cell phone, keep in mind that and actually this is true for laptop computers too, that what you're counting, or should be counting, is the time that they're charging. So that's when they're actually using the energy, when they're plugged in. When they're not plugged in, they're using presumably a battery, and that's not going to, we shouldn't count that here. So I charge my cell phone overnight, so it's 12 hours a day, and it actually draws energy even when it's fully charged. And we'll call this 365 days. And it's still a very small overall energy use for the year. And then finally down here, the process loads, which things like, as I pointed out before, the oven, that is gas and 7,300 watts. So I'm actually going to want to make a note that that's a gas oven, because that will affect the cost. And 7,300 watts, and say a half hour for probably once a week, maybe. That might be generous for me. I don't cook that often, so that's not that significant a load. However, when we go over here to the cost, we should be careful, because that is currently linked to the cost of electricity, not the cost of fuel. Okay, last part, and we're almost done here, is hot water heating. And hot water heating is something that we're not going to spend a lot of time on in this class, because it's actually a relatively constant number, even though it can be a relatively large number. And there's very few things you can do to make that a smaller number other than buy better equipment and or use it less often. And so I should say there are a lot of things you can do. There just aren't that many interesting things you can do. So there is a domestic hot water, DHW by the way stands for domestic hot water, tab. And if you come over to here, you can see yet another rule of thumb calculator for figuring out how much hot water you use and how much energy that hot water uses. I think I'm going to go through this in more detail later in the semester. For now, I would accept all these defaults. The primary one is whether it's an electric heater or combustion heater, and in this case, the efficiency is 80% because it's combustion gas. If it were electric, this would be 100%. The rest of this, let's just keep as is, and what this does is give you a energy use per liter of water. And then if you come over to here to the right side, this is the annual domestic hot water use. It goes by end use, and you can add end uses to this. These are the ones that I could come up with: shower, bath, laundry, cooking, hand washing, dish cleaning, and other cleaning. And assigns a flow rate in liters per minute, the time that it's on, so 5-minute shower, and that results in a volume. And so that's a formula right now. And how many times per year? So I take a shower every day. That's 365 days a year, or uses per year. And then the multiplier. If you have a roommate, then you're going to want to multiply that by 2 if they also take showers every day. If they take a shower every other day, but you take a shower every day, then 1.5 would be the right multiplier. Now this is an interesting one. Percent hot water. Keep in mind when you take a shower, it's not all hot water. It's a combination of cold water and hot water. And you can use these estimates, or you can customize this if you take particularly cold or particularly hot showers. And I've got a guide down here that will give you the percent hot water relative to the delivered temperature. So in my case, I take a shower that's about 40 degrees centigrade, and that's quite common for showers. and that results in 77% hot water use. If you take cold showers or lukewarm showers, a 30-degree shower would be 47% hot water. Alright, and then based on that percentage of hot water, we get a total volume per year per zone for the shower and then for everything else. And then the energy use is just multiplying the energy per liter times number of liters, and that's how we're getting the total here. So I would like you to please copy all of these. I'm going to press Control-C here and go over to Energy Model Template, and I'm going to right-click and paste the values. Actually, in this case, there's too many. So before I do that, I'm going to add a few lines here. I do that by clicking on the left, right-click, insert copied cells. Will that work? No, that's not what I wanted to do. What that did was just inserted all of the copied cells that I had. I'm going to try that again. Right-click, insert, and now I've got more cells there. Now I have to go back over here, copy these, go back over here, right-click under values, and so I've got them. I'm going to go back to domestic hot water. Now I'm going to copy the uses and right-click, paste. So that's an easy way of doing it. In this case, whoops, I copied this into the wrong area. These guys actually need to copy over there. So that populates it. So for the hot water only, don't fill out these cells because we've already figured this out using a slightly different method based on volume of water rather than power and time. I hope that all made sense. If it didn't, bring questions with you. So that's the gist of it. That kind of walks you through how to generate this energy model. And down here are the charts that are automatically generated based on that. And in the next tutorial and final one, I'm going to go through how to output these charts, and then the last and most important step, which is to annotate them.